Let's talk a little bit about springs, how they exert forces, and how they store energy. If I have a spring hanging from the ceiling like this, it has some natural length. We call that the unstretched length of the spring. It's natural length. And when it's sitting there like that, it has no energy stored in it, and it doesn't exert a force. It's the equilibrium position of the spring. And for our purposes, a spring can be stretched or compressed. When it's at its unstretched length, it can be pulled and stretched or pushed and compressed. We know in actuality when springs are designed, some of them cannot be compressed. The coils are already together. They can only be stretched. Springs might be manufactured in certain ways, but we also know that you could manufacture a spring that can go in both directions. So for our purposes, our springs have some space between the coils. They can be stretched or compressed. Now, if we take this spring and we hang a mass from the bottom of it, the spring will stretch by some amount, and it will exert a force on that mass. Well, what's the force it's exerting on our mass if the mass is just hanging there? Let's draw a free body diagram for the mass. There's a spring force pulling up. I'm going to call that F sub SP for spring. There's the force of gravity pulling down, the weight of the object, and our mass is just hanging there at rest. So those two forces have to be equal. The force that the spring is pulling up is just equal to the weight of our object. Our spring has stretched by a certain amount. The bottom of the spring was at the dashed line before, the equilibrium position or unstretched length of the spring. Now the bottom of the spring is here. We'll call that delta x, some change in length. We don't care about this length up here. What we care about is how much the length has changed. Now let's hang twice as much mass. Let's hang a mass with twice the weight of this mass. The spring is going to stretch some more. And what's the force going to be equal to when that mass comes to rest? It's going to be equal to the weight of the object. If we measure the length, this one, the length that this spring stretches is twice as much as the length that the other spring stretched. If we were to plot the force versus that distance that the spring has stretched, we would get a straight line. This is known as Hooke's law, that the force that a spring exerts is proportional to the displacement. I'm going to write it as the magnitude. We can write it as a vector equation also. The force is proportional to the displacement. So we can throw a proportionality constant in there. The magnitude of the force is equal to some constant times the magnitude of the displacement. That means it's linear, right? This is a linear relationship, which is what we see when we look at our graph. We see a straight line. And what is that proportionality constant? That's the slope of our line. We call that the spring constant. So that depends on the spring. Some springs that you've maybe played with in the past are really easy to stretch and compress. So they would have a small spring constant. doesn't take a very big force to cause the spring to stretch or compress. K would be small. Some springs are really stiff and it takes a big force to pull them, to stretch them, or to compress them, and they would have a large K value. This relationship is not always true. Most springs obey this relationship. Sometimes you don't want a spring to obey this relationship. You can design it with funny shapes or do other things to change the way the spring force reacts. And you also probably know that this line is not going to continue forever. At some point, you're going to stretch the spring to the point where it won't pull back anymore because you'll fatigue the metal or change the shape of the metal that the spring is made of. So this shape will probably level off, and if you pull hard enough, that spring will break and it won't exert any force. So if you keep going, it probably looks something like that. But we'll just concern ourselves with the location where the spring operates normally and has pullback and doesn't deform. Personally, I think this is the best way to remember Hooke's law. The magnitude of the force is proportional to the displacement, to the amount that the spring has stretched or compressed. It doesn't matter whether the spring is stretched or compressed, the force is proportional to kx. Some books write it this way. They write it as a vector equation. The force is equal to k times the displacement as vectors. But if you do that, what happens? Think about this for a second. We displace the spring in this direction, but what direction does the force act? The force from the spring acts in the other direction. So we need a minus sign here. If you write it as a vector equation, you need that minus sign. The force is in the opposite direction of the displacement. This is the spring force. Maybe I should put SP there. Spring force is equal to kx, the magnitudes, or if we write it as a vector equation, the spring force is in the opposite direction of k delta x. And I think we can all understand that springs store energy. If you push a block up against a spring and hold it there and then let go, that spring will push on the block, it will do work on the block, and it will change the block's energy, get the block moving. We call that spring potential energy. I'll use this symbol, U spring, SP, subscript SP for spring. Some books use an EL for elastic, but next quarter we're going to have electric potential energy. We're going to use an E for that, so I like SP for spring. Okay, let's take a look at the spring potential energy. If we have an object, a box, pushed up against a spring, and we let go of it, the spring will push on it, doing work on it, changing its energy, as I said. So we can calculate that. We'll make our surface frictionless. So all the work that the spring is doing is going into changing the kinetic energy of the block. So we've pushed the mass up against the spring, compressing it by an amount delta x. We let go, and at the instant the spring hits its equilibrium position, the block will leave the end of the spring and it will keep moving in that direction, and the spring will be left behind. What we want to know is how much work does our spring do on our block so we can figure out how much energy was stored in there. Well, we know that work is equal to force times distance in the most simplest case. When the force and the displacement don't point in the same direction, we make that a dot product. And you might be tempted to say, well, the force that the spring exerts is proportional to the displacement. And the displacement is delta x, so the work done must be k delta x times delta x, or k times the square of the displacement. But that would be wrong, because this delta x is the total distance. And this force, if we plug in the total distance our spring was stretched or compressed here, we get the maximum force. This is not the force at any given time. This is the maximum force. Right here, right there. That's the force the spring is exerting at that instant, right there. But as soon as this block starts to move a little bit, here, the spring is exerting a smaller force. And by the time the block gets to here, the spring is not exerting any force at all. The force goes to zero. But what do we know about the spring force? It's linear. So if we change this, so this is wrong. What we need to use is the average force that was exerted on our block during this distance. If we use the average force and the force is linear, well, that's pretty straightforward. It's just the average of the endpoints. One of them is F maximum, one of them is 0. So F maximum plus 0 divided by 2 is our average force, and we multiply that by delta x. And what is the maximum force? The maximum force is k times our displacement. So we get 1/2 k times the maximum displacement squared. That's the work done. A different way to do this is to treat the force as what it is, a non-constant force. So we wouldn't write work equals force times distance. We would write work is force dx over some tiny distance. Because our force is not constant, we would say over some tiny distance we could treat the force as constant, multiply the force by that infinitesimally small distance, and then what do? We add up all the little contributions. Now when we plug in kx for our force, and we're integrating from 0 to delta x, our maximum displacement, we get 1/2 kx squared evaluated from 0 to delta x, where delta x is the maximum displacement. The work done is actually a dot product, because in this situation, the spring force was pushing to the right and the box was moving to the right. I got a cosine of 0 degrees, so I just wrote it as f dx. But the spring force could be in the opposite direction. For example, if my box and spring were actually attached together, at this point, when the box passes the equilibrium position of the spring becomes stretched. And the spring, if the box continued to move in this direction, the spring would actually be pulling in the opposite direction. And the box would be moving to the right, and the spring would be pulling to the left, and the spring would be slowing down the box or doing negative work on the box. So really, I should have written this as a vector dot product. The work done by a spring on an object could be positive, negative, or 0. The whole point of finding the work done was to get the potential energy stored in that spring. So we know that the work done by the spring was 1/2 kx squared. So that's how much energy had to be stored in the spring at the beginning of the problem. So our U spring is 1/2 k x squared, or the displacement squared. This amount the spring was stretched or compressed. Now, the spring potential energy is always positive. It doesn't matter if the spring is compressed, it has energy stored in it, or stretched, it has energy stored in it. Spring potential energy is always positive. Just to summarize, the work done by the spring can be positive or negative, 1/2 k delta x squared. The energy stored in the spring, the potential energy that a spring could store, always positive, 1/2 k delta x squared.